So for those of you who may not be familiar with PKIC, we're up in Victoria. We're sort of an analogy to Climate Impacts Group or to OCRI, or Regional Climate Services Center up there. And I'm going to be talking about how some colleagues of ours in the Ministry of Transportation got excited about a 200-year flooding event and work that we did with them afterwards. There was a question earlier from a previous speaker about, how there's a lot of talk about giving climate information to stakeholders, but what about sort of that two-way interaction? So I'm going to try to get into that a little bit. First, I also want to acknowledge my colleagues, Steve Sobey and Alex Cannon, who worked on this project with me. And I also want to thank all of you for sticking around in the ballroom. I'm personally green with envy over the plum conditions downstairs in the billiard room. I wasn't sure how that pun would go over. I thought it might go over like a lead pipe. Hopefully I haven't gone scarlet trying to be funny up here, but apparently it cut the mustard. There's a few laughs. So anyway, this is an overview, and we're going to go to a 45-second animation. So Bella Coola is the case study we're going to be talking about. It's on the west coast. And these are some images from this 200-year rainfall a couple of years ago in September. There's 282 millimeters in 4 days. You'll see this slide again in the talk. So this had our colleagues wondering about how often is this going to happen. If we have a 200-year event, does that mean it's not going to happen again for 200 years? So I won't talk too much about the regional climate models and the work that we did, but just focus on the results. And here's just a gross oversimplification of sort of one result and what does that mean. So that's all I'm going to say. The rest of the talk is everything I just said, but in slightly more detail. So here is Bella Coola. You can see actually it is on the coast, but this is actually the end of this inlet here is 100 kilometers in from the coast. So it's actually not directly on the coast. It has some aspects of an interior climate as well. And so this is just a graph that shows the 4 days of rainfall in September 2010. And because Bella Coola is 100 kilometers in from the actual coast on the edge of this inlet, the average September precipitation is only about 84 millimeters. So this was quite a significant event. The rainfall on just the first day was well over the average for the entire month of September. And the total for these 4 days was, I mentioned, 282 millimeters. So here's a couple more slides on the impacts that we're seeing. You can see why our colleagues in the Ministry of Transportation and Infrastructure got interested in finding out, okay, is this really only a 200-year event that we can expect on average one every 200 years, or because of climate change, do we need to worry about this happening a little more often? And so now I'm going to go into a little bit of the more technical side of the types of stuff that we provided them. So this is a map. You can actually see that the coastline. This is the west boundary of the region. Here's the inlet here that Bella Coola is on the end of. And so you can see the darker blue is wetter areas, and this odd-shaped, like a weird balloon that someone would make at a fair or something. This region represents the highway region that they're interested in, because we were working with the sort of the highways department. And you can see the eastern portion of this region doesn't experience as much precipitation in the past as the other portion. So the images were mostly from Bella Coola, but there are also several other sections of this highway that were affected by that event. And it's the area that's of concern. So this slide is just meant to show the kind of risk management process that the ministry is undertaking. I won't go through it in great detail. If you're interested in it, you can find more about it. It has this great acronym, PIVC. No one can ever remember what it stands for, so I've spelled it out here, Public Infrastructure Engineering Vulnerability Committee. They've come up with a sort of a framework or protocol. It's one of many ways of conducting a vulnerability assessment. As engineers, they're very interested in combining both information on probability as well as severity. So what they'll tend to do is do this vulnerability assessment where they're imagining hypothetical events of various different severities, and the information they want from us is, can we try to quantify the likelihood of these events happening? So that's where we're really collaborating together with them. And this is one of the sort of end results they're hoping to get towards. On the right here, this is the projected change on the bottom of the 10-year return period precipitation. And so they're really wanting to get to a place where they can inform decision making and actually require all new highway projects to actually take climate change into account. And in order to do that, it's very difficult because there aren't any, engineers are very used to having professional standards. If there's something you have to do, there are guidelines on how to do it. So they want to move towards actually issuing, you must consider this 10-year return period. How does it affect your project? The purpose of the case study that was inspired by Bella Coola is how can we use the risk management framework to try to model some decisions so that we don't just leave engineers and new firms that are putting bids on highway projects, leave them in the dark. We want to give them some guidance. So the idea was to use Bella Coola and a couple other areas as guidelines. What I won't go into as this stuff, this is 95% of the work that we did was on the technical side, doing the downscaling with regional climate models. If you're interested in this, come to AGU. I'll talk a lot in gory detail about what kind of downscaling we did. I will just touch a little bit, though, on historical validation. This is something that's very important because, again, we were dealing with engineers. There was a big interest in, engineers are used to using a lot of modeling, but one thing they always do with their models is validate them. So this is just showing the historical simulation of our statistically downscaled regional climate model results over the course of the 20th, well, this is 1980 to 2000. And you can see quite a good correlation and a small sort of error. Partly that's by design because of the statistical downscaling, but it's still important to show because we're going to be looking at not just change in average precipitation. What they're really interested in is changes in the extremes, and so you want to ask the question, are these model results actually simulating the extremes well? And you can see, maybe I'm going to pick on one, which is Wharf G. That's the sort of probably the hardest to actually see, this light blue color. You can see it kind of stands out as a few cases as being quite a bit wetter. By and large, all of the models are doing a pretty good job. The reason I point that out is if you look at this same information, but now looking at it in this sort of bell curve where you're looking at along the horizontal axis, different magnitudes of precipitation. So further out along the axis, these are the more extreme events, and these are more modest events. So most typical rainfalls in a given day are around 10 millimeters per day, plus or minus. And so you can see that the precipitation that Bella Coola received in that 2010 event is way off this chart. But if you look at the historical simulation, you can see that all of the models are actually doing a pretty good job for most of the distribution. And I pointed out Wharf G. You can see it does tend to over-simulate a little bit some of the more extreme events. So this is just pulling out what we saw on the previous slide. Okay, so in terms of the future then, after we get past the historical validation, this is just showing the precipitation throughout the year in Bella Coola. As I mentioned, it's got aspects of both a coastal climate and an interior climate, and especially because this is an average for the region, which includes that there's sort of two parts to the region, one being a little drier and more interior climate. So you can see that there is this sort of Mediterranean west coast, wetter in the winter, drier in the summer, but not quite to the same scale of, for example, near Victoria, Vancouver, right on the coast where we would get much drier summers. Now the gray shaded area is the projected change. The blue line is the historical precipitation. And you can see that there's some range of uncertainty, and sometimes of the year we have just as much of projected increase as decrease. But throughout the winter and spring and into early summer, there's increased precipitation projected. Now this is just the 30-year average change. What they're really interested in was the extremes, and so here's just an example of one of the tables of extremes that we showed. I've highlighted in red that one number that was in the cartoon that I showed at the beginning of 36% increase in the 25-year event. You may ask why we're looking at 10-year events and 25-year events when what happened was a 200-year event. We're limited by the amount of data that we have with the regional climate models. They're limited to 30-year periods in the past and the future. So a 25-year event is really as extreme as we can get. But you'll notice, though, that as you get more extreme, the percent increase is tending to go up. And this is something that's actually not surprising from just from extreme value theory, but it's interesting to see this concretely with numbers. So an increase of only 11% in the annual total is associated with 20% in the 5-day cumulative precipitation, which is more likely to actually cause damage. Also associated with 31% in the 10-year extreme, and again 36% in the 25-year extreme. So the idea is that engineers would take the 10 and 25-year events as sort of you would expect at least that much change in the more extreme events. So in terms of looking at future precipitation projections throughout the region, everything I've just shown, like on the table we just looked at, that was averaged over this whole region. And so this slide is just to point out that we are looking at a region, and the response throughout the region could differ. What you see on the left is the winter precipitation change, and on the right, summer precipitation change. This is in terms of percent increase. So we actually find a larger percent increase in the eastern part of the region, even though there's less. If you looked at total amount of millimeters of increase in precipitation, you'd find less in that part. But because it was drier in the past than the western part, the percent increase is larger. And also, this is the summer, and you saw throughout some of the summer months, some of the models project as much of an increase, others project a decrease. This is the ensemble average. And you'll see that sort of uncertainty reflected spatially here. Generally, there's an increase projected, but just south of the region, we actually have decrease projected in the summer. So it's something to keep in mind. And then finally, this slide is just showing that one of the things that was of interest to our colleagues in the Ministry of Highways, they have specific pieces of infrastructure that they're concerned about at specific locations. And when you get down to that level, then they really wanted to work with something like the 10-year or 25-year extreme event. And at this point, they don't just want the percent increase. They really want to know how much more water do I expect in terms of millimeters at this location. So we're able to provide, through the downscaling, we're able to provide a range of change that is specific to each of various locations rather than just having to rely on the regional averages that I've shown so far. And that's it. My summary just harkens back to the cartoon we watched at the beginning. There was a lot of water that fell in Bella Coola that freaked out our colleagues and had them at first asking questions like, can you tell us if this was caused entirely by climate change? I mean, the questions were more on that line at the beginning. And it took a couple of years of working with them to help them understand the uncertainties that are present in the climate models that we have, and for more importantly, I think, for us to understand what they actually needed. And we're now at the stage where we're able to provide some results from climate models and from statistical downscaling that can be used to help inform decision making. That's it.